All right. Hello, everyone. This is your TA, Matt, here with the video for discussion for week 7, right at the top here. So, based on office hours and the like, I think the undecidability stuff is probably the most confusing. So, today we're going to talk about the undecidability of ATM. Just for quick reference, the language ATM is the language of all Turing machines and a string, such that M is a Turing machine here, and M is in the language of M. So in other words, it's the language of acceptability. So that's why it's kind of it's sometimes called the acceptance problem for Turing machines. So determining if some given string W is accepted by a Turing machine M. Remember, Turing machines can have a string representation. And yeah, so deciding whether or not that belongs there. So it should be clear by now, I think, in this stage of the course that there are some languages that are not decidable. So if that's not clear, I would say that is a prerequisite to this video. You can maybe comment on EdStem if you want to see the math behind the difference in sizes and the uncountability of languages versus the countability of Turing machines. But yeah, I will say that's a prerequisite. So you should be familiar with the fact that some languages are not decidable. So the goal of this video is to work up to this proof, which I actually think is pretty hard. It's pretty short if you just look at it straight up, but I think to understand it, there's some ideas that we need to dive into. So this will be the goal of the video, is to build up to this here. Okay, so in order to build up to the ATM language, I want to start with a different one, actually. So I'm going to erase this for now. And we're going to start with a different language that is actually a subset of that language. So we're going to start with this ASR idea. And it's basically going to be the language consisting of Turing machine string representations, where M is a Turing machine. And the string representation of M is accepted by M. So what that means is the string representation of the Turing machine is in the language. So it's just like the Turing machine accepts its own string. And that should not be too much of an ask, since you are familiar with programming, and a program is just like a text representation, right, in the programming language, and then you can run that text implementation. So to distinguish this from ATM, note that, let's see, maybe blue. So here, there's no W, right? Because we are selecting the string we care about. So it's only for this string, which is the string representation of M. So it's a specific string we're talking about here. And this will lead us to the more general problem of arbitrary strings. So the difference between this and ATM is that we're talking about a specific string here, right? So we're only going to accept M's where the string representation of M is also in L. So I think it's probably a little bit more precise to use parentheses here, just to kind of illustrate the difference here. So M is a Turing machine, and it's only going to be accepted if its string representation is in its language, so it accepts its own string. Okay, so like kind of self-reference. That's why I call this SR. So this is like the self-reference acceptance problem. Self-reference. Okay, so we're going to be talking about this language first. So let's get some room here. Okay, so let's first talk about, I think to get more of a like a frame of reference here, I really want to talk about what makes this problem hard. So let's maybe right over here. So I'm gonna move my mic. What makes this hard? Because I don't think it's obvious why this self-reference problem is so important. Okay, so I would first like to talk about this string representation more closely. So I'm going to just write some Python pseudocode here. So let's say we have some function called like an interpreter, and this function takes some program, maybe like a class you can envision, and it has like a stream of instructions or something, and it just like runs the program. Okay, so maybe it's like iterable, for maybe for like instruction I in P, you just like do stuff, right? So just run the program, run I with I. So you just kind of run the program, right? So this is kind of like a TM, right? So let's maybe here, so kind of like TM. Because it just runs some text, right? It's doing some operations over some input, right? So the dichotomy I would like to illustrate here is that programs have a text form, and TMs, I guess, programs/TMs have a text form and a like corresponding run, right? So, and a runnable form, I guess. I mean, this doesn't really make a whole lot of sense because a text form is technically runnable, but hopefully you get what I mean, where there's like a text, like a very finite text formulation of the program, and then something that can be run, and that run can potentially take a really long time, right? And more precisely, what I would like to look at, so maybe we can use a color here to delineate the function, is when you call interpreter. Actually, I don't like that color a whole lot. Let's go back to white, a little more visible. So when we call interpreter with itself, this is like the self-reference problem. So hopefully in your mind, it's not too big of an ask to jump from like this acceptance problem where you have a TM and a text input of the TM to this problem here where you have like some function or some program that runs, accepts as input other programs, and then you were to like call itself. Okay, so these are analogs, essentially. This is kind of the mental model to have. This should maybe hopefully make some sense, right? Like you run a program with its own text. So this should remind you of recursion, right? So and that, these ideas should be all similar to you, or you have like self-reference, recursion, so maybe we can kind of use recursion here now. And importantly, this is not always a problem, right? I'd really like to stress that. Recursion is not innately like a bad thing. So it's not always a problem. And what I mean by that is it's okay to like have an interpreter that accepts its own input, right? Like this is fine. So even, for example, in this example on the left here, if I say for I and P, just like, I don't know, print I, then this would just print out these same instructions, right? It's not going to do anything wrong necessarily. You really only start to get into issues when you do something like this. So if I were to define interpreter on the program P, and I were to run P, okay? And so this means essentially you interpret P as instructions or as the Turing machine, right? And you perform them. And like perform them, right? So this is like running, like simulating a Turing machine, right? So now hopefully this gives you an uneasy feeling because like we don't know if P is going to halt or not because of the halting problem by now. And so this is when things get dicey. And I believe this is where the original ideas come from for undecidability, and this problem of self-reference is exploring when precisely this becomes a problem. Because you can imagine that you have some recursive function that just iterates down each time, like summing 10 numbers or something. But like, what if P doesn't halt, right? So what if P doesn't halt? So this is only vaguely related to the problem we're solving, but I'm trying to get these ideas into your brain of like when self-referential ideas like become a problem, right? Okay, so more particularly, we're going to be looking at this case where interpreter calls itself, and what does interpreter look like? Okay, so let's say interpreter. So when we have interpreter and this thing that's going to like perform operations. So now let's redefine this to always run P and then do stuff afterwards. So now when we have this self-referential problem, interpreter calls like itself, right? And it's going to run interpreter. Okay, now things get dicey, right? Because I'm like trying to run this thing, right? And I could just infinitely recur, right? And you can now see why this would not halt. This is just like an infinite loop, right? So this now becomes a problem when we try to run things, right? And so this does not have an answer, right? Like if I were to call interpreter with interpreter, and what interpreter does is run itself, it infinitely loops, right? So this is now running interpreter, right? If we kind of like connect the parameters, right? Because I'm passing interpreter, which is just a program. I'm passing it to itself, and I'm trying to run it and interpret itself. So this does not have an answer, right? That should be clear to you. Does not have an answer. This problem here, when you try to run yourself infinitely, right? It's just always going to keep going down. I'm sure you've maybe written some infinite loops using recursion, and this is pretty similar to you. Okay? So now let's go back to the proof, because this idea here, this ASR, M is a Turing machine, M is in the language of M. If this is decidable, that's a huge claim, right? So I'm going to erase this over here, and we're going to keep that little idea on the right, because this is a huge claim. Because what this is saying is, if this is decidable, right? So remember, we're trying to prove undecidable, or maybe we're just exploring. It doesn't really matter. So if it's decidable, though, then there exists a Turing machine. So hopefully, definition of decidable is clear. It means the language is both recognizable and co-recognizable, and therefore a Turing machine exists that always halts for rejection and acceptance, right? So if that's not clear, probably review that a little bit before continuing. But what it means, if we were to assume this is decidable for the sake of contradiction, I mean, the contradiction is not clear as of now, but that's where we're headed, just to give you a heads up. But if we assume it's decidable, then there exists a TMH. And what that H can do is the H can like take a Turing machine and determine if it accepts itself, right? We're saying this exists, right? So if ASR is decidable, a Turing machine that decides this language exists. So what that means is there exists some H, and H of M will tell whether M accepts itself or not, right? And that's a very powerful claim, okay? And we just saw that this claim is probably like gives us an uneasy feeling because of cases like this, where you have a Turing machine and interpreter and Turing machine should kind of be synonymous in your minds right now, where they like run themselves, okay? And that's where the contradiction comes from, because we know there can't be an answer to this problem, right? You cannot run yourself if what you are is running the program, right? And it's kind of cyclical, but these are cyclical ideas, right? So it's like self-referential. But okay, so what the claim is from this ASR is that if it's decidable, this exists, and it can tell whether M accepts itself or not. So the challenge then, so what's the challenge? Is construct M in a way that makes this impossible. Okay. And the reason we need to construct M in a way, and this is maybe don't think about this as like a pattern among all problems, because the archetype of the problem when you do reducibility is slightly different. So just for this problem, bear with me for a second, but it should be clear that this claim is extraordinary, right? That we have a decider for any arbitrary Turing machine. We can tell if it accepts itself because of this self-referential idea that we just explored, where you cannot have an answer if what your Turing machine does is run, right? Okay, so what does M look like? Maybe you want to pause and think about how you'd construct it. I would be extremely surprised if you could just come up with this on your own without looking at it ahead of time, because it's very difficult. This is a difficult proof, which is why I'm spending so long on it. But I believe the ideas are important. Okay, I'm going to continue now with how to construct that M. Okay, and it should be clear that the goal is to hit the self-reference, right? So we want to hit this self-referential problem. Okay, so let's now construct TMD. So this Turing machine D, we're trying to reach a contradiction here, right? Because we're assuming it's decidable. We're trying to show that this is not actually possible. We're going to construct TMD, and this D is going to use M. Okay, so the idea is to use use H. It's going to use this H, which we know is extraordinary, and show that it's not possible to infer this answer in the self-referential case. Okay, so D must take a Turing machine, right? Description. So this is like a description. So maybe I can make that more clear using the angle brackets. Okay. So this Turing machine we're going to create to exploit H, this decider that we know cannot exist because of this self-referential case. So we're going to be really mean to this decider. So this TMD is going to use this decider. So we're going to use H. I'm sorry, maybe run. Because we know we have to run, right? Run H on M. Okay. So the goal of D is to pretty much look similar to interpreter here, right? Because we want to exploit the impossibility of deciding self-referential, like self-referentiality, or maybe there's a better word for that, I'm not sure. But the end goal is going to be to run D on D such that we get a contradiction. Because we just saw that running an interpreter or like a program with its own self and its job is to run that thing is impossible because we recur infinitely. So this is the end goal, is to reach this state where this is not possible, because that'll prove that the language is undecidable and this H cannot exist, right? But this H is like cheating. It's saying, okay, I can run that and I can always tell you an answer. So that should raise red flags in your head, right? So if I run H on M, envisioning the case of self-referentiality, right? That would be like giving an answer to this problem over here. So that is the key thing to understand, is that assuming H exists and then like running it on itself, you kind of have to envision that we were to pass D to itself, would be like having an answer to this problem. So that's what all these proofs are about, is like there's an unanswerable thing that the decidability assumption is mistakenly trying to do, right? And so what this is about is exploiting that thing that cannot happen, right? So if we run HM envisioning that it's self-reference, we can always make this wrong by saying if this accepts, because remember, it's decidable, so it always has an answer, then just reject. And if it rejects, accept instead. I'm going to quickly see if I can expand this a little bit. Okay, there we go. Perfect. So there we go. So maybe a little bit more. Yeah, it looks visible still. So where were we? Okay, so we constructed D here. Like that. And what it's going to do is, with the goal of exploiting this self-referential case in mind, because we kind of brainstormed and saw that this was a problem. If we run the decider, which basically tells us the answer to this problem, which we know is not possible, and then in D, to make sure that we're exploiting the fact that it's impossible, we just flip the answer, because we know you cannot know the right answer, right? Because of the self-referential case. So if it accepts, then we're going to reject to be mean. And if it rejects, we're going to accept. We're just going to do the opposite to prove that you don't know the answer, right? If that makes sense. So now what happens in this end goal of the self-referential case? So if we pass the string representation of D to itself, we're going to run H on D, right? And we know that H decides, so it always comes to an answer, which we know is going to be wrong, but the decider doesn't know that yet. So there's two things that can happen here, right? So there's case one. The decider can say, okay, it accepts, in which case we are going to reject here. Rejects. So we're going to reject on this second stage if it accepts, right? But isn't that a contradiction? Because you just said when H of D runs, which is, remember, just running D on itself, right? So we have a decider HD, which tells us if D accepts itself, and you said it accepts, but doesn't it reject because of the thing after? So what this is exploiting is the fact that we know, as the people constructing this D, you cannot know the answer. This H decider cannot know the answer because it's undecidable. This self-referentiality problem really makes it so that you cannot know this answer, and you claim to have an answer, but we always just reject after that decider because it must exist, right? And so what's case two? Case two is this decider says that, okay, when D runs on itself, it accepts. So D accepts itself, right? The decider doesn't have to run it. Keep that in mind. I don't like that I said the word run, but keep in mind the decider exists So it can solve this decision problem of knowing whether D accepts itself or not, right? And so it came to the conclusion in case 2 that it's a reject. But we know now that what D on D should do is accept, right? So we're going to go into if reject accept, right? So we're going to accept down here. And now that's a contradiction, right? Because you said that D run on itself is a reject, but I just ran D on in itself and it was an accept, right? So another contradiction. So these are both contradictions, and therefore this decider cannot exist. That's the conclusion, that since this is the wrong in both cases, there cannot be a decider for this problem, right? Of running a Turing machine on itself and knowing the answer, like deciding that answer. Because if you were to do that, since I'm self-referential, I can just flip it at the end, right? So it all comes down to this self-reference. This is the issue. And this takes a while to sink in. I'm not going to lie. Maybe my explanation was not the best, but it is a hard problem. And you need to understand this language before you even try to understand ATM, because ATM is a more general form of this. So sit with us a little bit, ask questions on EdStem if it doesn't make sense. But the key idea is to have this self-reference problem in mind, right? A Turing machine that accepts itself and tries to like run, and knowing that this cannot have an answer. But if the claim is that this is decidable, then this decider exists which can decide that answer. And that's where you should seek the contradiction. In order to prove the contradiction, you construct this TMD that exploits that fact, right? Looks just like our interpreter, where we're going to run it, and then after it's done running, because it can run. The difference here is that because of this decidable claim, we can run the decider. Deciders can always run and they have an answer. Since it always has an answer, we can just flip that answer and make it wrong, if that makes sense. So then this here proves that ASR is undecidable because there's a contradiction in both of these cases where the decider outputs, right, for this Turing machine here. So because I could construct a Turing machine, which is plausible, right? This Turing machine does exist, but this decider cannot exist for it. Therefore, this language is undecidable. Okay. So with that in mind, let's go ahead and jump to ATM. Okay. So let's look at ATM now. So this is the language where we have a Turing machine M and a W, such that M is a TM and W is accepted by M. So it's in the language of M. Okay. So this should now be very easy to do for you if you understand that previous problem, because the difference here is this is an arbitrary W. But we just showed that this problem is undecidable when this W is actually just when W is M, the string representation of M. So we should just be able to use the M string representation as W, right? And that would just prove it. So now let's look at the proof for ATM. Okay. So once again, this is a contradiction. So for sake of contradiction, assume ATM is decidable. So then H of MW exists, deciding ATM. However, let's consider that same machine we made earlier. Consider TMD. So you make this Turing machine D that's going to use M, which we know from before cannot exist, right, for some cases. TMD, and it can take a string representation of a Turing machine. Remember, it's like the interpreter we're creating, the TM we're gonna exploit. So in mind, remember from before. So keep in mind, we're gonna exploit using this in the end. That's the goal, right? So in order to pass itself, we're going to run H. So the key difference here is that this H requires a Turing machine and a string. But we know from the previous problem that the self-referential problem doesn't work, right? So when we run M on itself, right, like this, then we can just basically create the same D as before. So if accept reject, and if reject, accept. Okay, so same as before, because we know that once you hit the self-referential case with D in particular, this is not going to work. So now let's see what happens when we actually run using, so when we do D on D's own representation, right? So we're going to run M on itself. So then we know that H decides whether or not D should accept itself. So we have an answer, right? So we're going to run HD on itself, which is going to tell us an answer, right? So it's either going to say reject. So if it's reject, then we will come over here. So let's say, sorry, let me write this a little bit better. So let's say this is reject. So this is like case 1. Then we look over here and we say, okay, well, actually we accept in that case. Sorry. Which this is a perfectly valid Turing machine, right? And it's exploiting the fact that H cannot exist and doesn't work for the self-referential case for this Turing machine, right? But in this case, doesn't that accept down here? Which is a contradiction, right? Same as before. And then let's say in the other case, so this would be case 2. So let's say case 2, where this accepts. Sorry, I'm kind of running out of room here. Where this accepts, then we know that if we accept, we should actually reject, right? Then reject, which is now a contradiction, right? So it's the same idea as before. We just made this one step of isolating the W to the case of self-referential strings. So it's using a subset of W for the self-reference one. And you can actually show that this reduces to the other problem, because you can just say, well, ASR is undecidable. Therefore, ATM is undecidable by doing something similar. But I hope this makes it more clear, building up to this ATM idea and showing how this construction of D came together, because it is kind of backwards, right? You kind of have to envision the goal of getting the self-referential part in the end and showing, okay, I know that's impossible using my knowledge of like recursion and looping and halting. And so how can I construct something that exploits the fact that the self-referential case is impossible, right? Well, you just run the decider on the self-referential case as we did before and do the opposite of what the decider tells you, because you know the decider can't possibly know ahead of time, right? That's how the exploit works. So I hope that's okay. Maybe we look at one more, just more concrete example. Maybe we look at halt. So maybe I can just erase this for now. Zoom back in. So let's look at halt TM. So we're going to say this is the language where M and W and TM M halts on W. So what that means is reaches Q accept or Q reject. Okay. So what's the strategy? So we know that if this is decidable, then H exists. So a TM H exists, which decides halting. So doesn't that seem like a huge ask? So what's a Turing machine that can take advantage of the fact that H cannot possibly exist, right? Well, I think it's actually pretty straightforward. So we just construct TM, let's call it M this time for Matt, where the first step is we'll run, you need to kind of specify what the parameters are. So this will take a M and a W, or maybe I won't use M then. Use D again. Okay, so we'll run H of MW, because remember, H decides the problem of whether or not this string will halt on M, right? So run that. This will decide halting. Okay, so there's only 2 options that come out of this, right? So option 1, maybe option, so 2, if reject. So if it does not halt, then we know we should reject. Then we reject. So we report that this thing doesn't accept. And then down here, if except, now we know it halts. So then we can say, okay, if except, then run M on W, which halts, has to halt, right? And now if that accepts, we accept, so we report accept. And if reject, we reject. So now what does this TMD do? Well, this TMD decides ATM. Which we know is undecidable. So we know that if halt were decidable, then we could construct a TMD that uses that thing that's impossible to exist. Well, we have a feeling is impossible to exist, right? To solve the unsolvable, right? We proved that ATM was undecidable. And so if this H were to exist and decide halting, then TMD could exist using this methodology and therefore prove that ATM is decidable, but we know that's not the case, right? It's undecidable. So then this problem reaches a contradiction because we know ATM is undecidable, right? Because of the proof I just showed you. So that's the proof that halting is undecidable. A little easier, right? But the case is still the same, where you like basically construct the exploitation, right? So in this case, this is more concrete because this is a reducibility problem. So we're reducing ATM to the problem of halting. So we're saying if you can solve halting, then you can solve ATM, right? So this is more, that's why this problem I think is easier, because the goal is more clear immediately that we are going to try to solve ATM. So we just need an arbitrary decider, and halting allows us to do that. But the previous problem, I think the goal is not clear, that we're targeting that self-referential impossibility. So I think that's where the confusion comes from. Okay, so that's about all I had. I'm not sure how long this is going to be. I'll probably take a look at it and maybe upload another video or talk on a discussion or something. But most likely that's all there is, because this is a lot. I think this is a really hard problem and is very core to understanding the rest of the course and like the pattern of how to use these deciders that can't exist to exploit, right? To like make a TM that solves either an undecidable problem or reaches a contradiction, right? Those are both reaching contradiction, right? Either going to an undecidable problem or just that self-referential case. Okay, so yeah, thank you for watching, and I'll see you again next week, hopefully.